Hello. Sorry for the darkness. It should clear up in just a second. What I'm going to do, this is Prof. Nanias, and what I'm going to do is I'm going to give you a brief review of basic integrals so you can go ahead and start the course. The reason I'm doing that is last year, actually, when I taught a course, Calc 2, many of the students needed a refresher on the basic properties of integrals in order to follow. So what we're going to do is we're going to have an introductory video that you can view over and over again. So without further ado, let's go to share screen. And let's go to Ladybug. And so right here, what I'm going to do is I'm going to go ahead and do some of the basic integrals that you need. Now, first of all, let's do a review of integrals themselves. And for our purposes, there's two types of integrals. The first integral that we're going to encounter is the indefinite integral. And its answer is going to be a function plus a constant, where the derivative of this big function here is a little one. And this is called the indefinite integral. And you do need the constant, because if you remember from calculus 1, the derivative of a constant is 0. So if you differentiate the right-hand side, the derivative of the constant is 0, and you do get that. And as I said, it's a indefinite integral. As far as and examples of this, and I'll give you some basic ones. For example, if you have an integral of x to a constant power, where n is not -1, this will be x to the n plus 1 over n plus 1 plus c. And the integral of 1 over x dx is going to be the log of the absolute value of x plus c. So those are two very basic integral formulas that we'll be using throughout our course. And remember, the derivative of the right-hand side is going to be the function you're integrating, sometimes called the integrand. So that's one type of integration here. And I know I'm lying a little bit, because if you ask a more advanced mathematician about integration, they might talk about Riemann-Stieltjes or Lebesgue, but ignore all that for right now. We're going to view types of integration in terms of definite and indefinite here. Other key integrals. The integral of the exponential function is itself. We're going to get into e to the, and you can also say that e to the ax, you can view this as a basic formula. So these are nice to know, part of math literacy. And then it's some of the key trig functions. The integral of sine of x is negative cosine of x. Because remember, if you differentiate cosine, you get negative sine, so you need the negative to account for that. And of course, the integral of cosine of x is a positive sine of x. And using our differentiation formulas for trig, see if you remember what this is. That's integral of secant squared. Can you think of the function whose derivative is secant squared? And the answer, of course, is tangent. And then one other one that's nice to know. And these are just really derivative formulas in reverse. That's going to be the secant function. Because the derivative of secant, and let's just go over that in a second. Derivative of secant is this derivative of cosine to the -1, which by the chain rule times derivative of cosine is negative sine. The negatives cancel, so you end up getting sine x cosine squared x, which you can rewrite as sine of x cosine x times 1 over cosine x. And of course, this is your tangent, and this is your secant. Okay. So remember, indefinite integrals are basically differentiation in reverse, but you do have this annoying constant, which is important. And you can tell if an integral is indefinite because there's no numbers on the sign, no integral limits. Okay. So that's the first kind of integral we're going to talk about, is an indefinite integral, and we'll be doing a lot of these. Now, if you notice, there are several functions I did not integrate, and we will discuss those throughout the course. But this is a nice little basic, what you need to know, right? So that's one. The second type of integral will be something like this: a to b f of x dx. This is a definite integral. And for now, what we do is we assume that f is continuous on a closed interval. And it turns out that you don't necessarily need to know that f doesn't necessarily have to be continuous. You can relax that somewhat. Like, for example, if you integrated the function, let's say from 0 to 2, where f of x is going to be x from 0 to 1, and let's say x squared. If you drew a graph of that, the function would go like here, and then you'd have this. This would be the x squared part. This is just to be the plain old part. And well, actually, that is continuous, come to think of it. Yeah, I just kind of messed up trying to, let's make that -1, sort of drive this down here like this. Yeah, I just gave you a continuous function. That was a bit of a fail on my part. So let's make this a function that actually is piecewise continuous. So this is 2 and 3. So then what you do to solve this problem is you'd integrate from 0 to 1. And then you add 1 to 2, and you do the second integral over this part. So you can break this up like that, right? But for the most part, we're going to assume that f is continuous. We'll break up our intervals so that it is. And by the fundamental theorem of calculus, the integral of, again, assuming f is continuous, it's going to be big F of B minus big F of A, where f prime is equal to little f, and any antiderivative will work. So that's what the fundamental theorem of calculus says. Now, I could probably go over a quick proof here, but I think I'll skip that for now. But how that works is, let's say we want to integrate, let's say from 0 to 2, and let's integrate x dx. The fundamental theorem of calculus says we have to find the antiderivative for x. well, we know that this one works. And we evaluate that between 0 and 2. That's going to be 4 over 2, which is 2. And that's basically, basically that's how you evaluate the definite intervals. You just find an antiderivative and you plug in the things that work. And I should mention that this again is a theorem. It's not, not, sometimes you might call it a trick that works, but it's a pretty neat trick, and it's mathematically proven. Let's do a couple of others. And then we'll remark about this a little bit. Let's do some trig intervals. Let's integrate from 0 to pi of sine of x dx. Now let's see what that is. Antiderivative of sine is negative cosine. And let's evaluate between 0 and pi. We have minus cosine pi minus a minus cosine of 0. Parentheses helps here. That's minus 1. Minus a minus is a plus. Cosine of 0, which is a positive 1. That works out to 2. On the other hand, if I decided to go from 0 to 2 pi sine of x, well, minus cosine. But if you plug in 2 pi, you're going to get the same thing as you plug in 0. So this has to be a big fat 0 here. Now, why is that? Why do you get a 0 when you integrate from 0 to 2 pi, but you get a 2 when you only integrate here? Well, that's one of the reasons definite integrals are such a big deal. What a definite integral gives you for a continuous function, it gives you the area with sine of the region bounded by the graph of f and the x-axis between x equals a and x equals b. So the way to think about this, let's say this is x equals b. That's hard to read. And let's say this is x equals a. What the integral is going to give you, and this is your function f, the integral of f right here, well, the integral of f, I'll just state it. It gives you this positive area, and you take away from that this negative area. So, addressing this, let's just let's label these. Let's say this is area 1. This is area 2. This is area 3. The integral from a to b of f of x dx will give you area 1 plus area 3 minus area 2. So the area below the axis gets subtracted. These two areas get added. Okay. Now let's do just a little bit of an exercise. Let's call this integration without integration to see if we got it. Now we're going to learn to do this integral by formulas, but this is an integral you can do right now if you know what you're doing. Let's try to, and this is an exercise I'll close the video with. Let's say you want to integrate from 0 to 5 of the square root of 25 minus, What does this equal? Well, let's see. If you look at what we're integrating, let's write this as y. And let's do some algebra. Let's square both sides. And then let's add x squared to both sides. And we see that this is a circle, radius 5. See that? So it's a nice circle of radius 5. So, of course, we're not going to be getting the whole area here, because remember, the x values go from 0 to 5. So if you plot this, this is 0, 5. This is 5, 0. This area is given by this interval. This is, well, the area of the whole circle is pi r squared, but you only have a quarter of it. So it's 1/4 pi r squared, where r equals 5. Right? So this is going to be 25 over 4 pi. And that's going to be what this integral is right here. And notice we didn't do it. We did no fancy substitutions. We didn't do any fancy techniques. We were able to figure out that this is just a quarter of the circle. So anyway, that's a little bit of a review for integrals. You know, obviously we're not going to, introduce material at that speed. But I figure these are the sorts of things that will get us going, and I'm going to go ahead and post that as a review. And looking forward to seeing you on actually a week from tomorrow. Have a good day.